Hi everyone. In this video I'm going to explain how we derive the equation to find the radius of curvature for our spoon when we go and look at the case for the two types of mirrors that we'd look at with the spoon. So if you recall, spoon has this particular bowl shape in this particular nature. It usually has a very long axis here and a shorter axis along here, which we'll define as the semi-major and semi-minor axes respectively, by assuming that the overall shape of the spoon is elliptical. So what we'll do is we'll take the toroid, and specifically the torus, which is essentially a circular cross-section of a toroid. You can have square cross-sections of a toroid, and so on and so forth. So the specific type of toroid we're going to be working with is a torus. And as an example, you may be very familiar with donuts, even tires. Well, to some extent, tires kind of have a torus shape, but overall they have a toroid. They're classified as a toroid, but donuts are the go-to example for a torus. Everyday, real-world shape that you might be familiar with. So what we'll do is we'll take a planar cut or planar section of our toroid along the side here. And here I try to draw essentially a elliptical shape with the semi-minor and semi-major axes and some depth or height of the dome that's created. So basically we take this section that's being cut off by this plane and we lay it down flat. We see that we get a dome and basically an elliptical shape as the base of that dome. All right, depending on how you're viewing this, if you look at the cross-section of the donut tube itself, you'll find that the semi-minor axis corresponds to that cross-section here. So this chord that is being drawn here with the height h of the dome shows that. The semi-major axis of the ellipse comes from looking down onto the donut shape itself, where we place the plane along that side of the donut itself. Right? And so the radius of curvature that we would effectively want if we go and find for the semi-major axis will correspond to this radius of curvature. If we use this semi-minor axis, the radius of curvature will correspond to this one here. So you'll get two different radii of curvature depending on which axes you are using. So when we combine those two, we then get this elliptical dome shape. All right. So to work with the chord itself, it doesn't matter exactly which one we're working with. The chord relates to a circular shape, and whichever circular shape you're working with, there should be a chord that will give us that particular that will come from whatever semi-major or semi-minor axes we measure. What we'll then need to only determine in relation to that is what is the height or the depth of our spoon being measured from the edges down into the bottom of the bowl. All right, so these will be things that you'll have to determine, basically either the width or the length of the spoon bowl, and also the depth of the bowl. Here in general, I've drawn out a circle with some radius r, and that sweeps out a particular arc angle s here. All right, so arc angle is just radius times the angle in radians. Here I've simply bisected the full angle theta with essentially the radius r here down the middle through the middle of the chord to make a right triangle that we'll effectively use as a means of determining the radius of curvature from the chord and the height. Okay, so this should hopefully show you the equation of finding the chord itself. If you're interested in ever finding what the chord is, this is how it's given inside a circle. So, as I stated before, the main goal of this exercise is to determine what the radius is from the chord and the depth of the spoon bowl itself. So first we'll start with the first triangle that's made here, with the radius being angled off of this bisected line here by theta over 2, or half the angle. We then make the base, or define the base to be of length L, and we'll know that the side of our right triangle is half the chord. Right, so this will play an important role in how we determine that. So what we can then deduce is that the full radius that's made is equal to the length of this triangle that's made plus the depth or height of our spoon. Okay, so then we can rewrite this length here in terms of the radius and the height. So now that leads us into then using this triangle to then apply Pythagorean's theorem to get ourselves a second independent equation here that relates the radius of curvature and the length or the length of the base of our triangle here, so that we can then solve for this value here, the length of the base, in terms of the radius of curvature and the two other quantities that we will determine just by simply measuring. Right? So using Pythagorean's theorem, we can then deduce that the hypotenuse of our triangle, which is the radius, is equal, the square of that is equal to the base squared times the side squared. And so we get this relationship, and if we solve for L squared, we get, if we put this in terms of L squared, we have another relationship of L that comes from here. We can square that in there and then substitute that into our Pythagorean theorem derived equation right here. Right? And so we basically now have an equation that is of the radius of curvature, r, and of our known quantities, the depth of the spoon and the one of the axes of our ellipse for the spoon. So then solving through hopefully some simple algebra here. I kind of skip a few steps a little bit, but effectively what we get is this relationship here. And for my particular spoon that I was using, I get about 7.1 centimeters. And what I'm going to do next is sort of show that this relationship should be valid if you're unsure as to whether or not it is okay in that derivation. So I just did a second independent analysis. You can certainly stop the video here if you're not that interested, but certainly for those that may be curious and want to take a more advanced approach in determining the radius of curvature, what we can then do is use the arc angle in addition to the chord itself in order to solve for the full angle theta. And then from theta we can then figure out what the radius of curvature is based on the arc, the arc of the angle itself. This would require an additional measurement of determining what the arc length of the spoon is rather than the depth, but the chord would be known in that particular instance for that. All right, so here I basically take the ratio of the chord divided by the arc length, and we get this equation here. And simplifying it in terms of theta, I then substitute theta over 2 for alpha just to make the writing a little bit more simple. All right, so for those that were wondering, the more advanced case requires us to use a bit of calculus. In this case, we'll be doing the Taylor expansion of sine alpha. All right, in terms of alpha. Technically, this is the Maclaurin expansion, but that's for discussion in math courses. Typically, we just call it the Taylor expansion, even though we do use the Maclaurin expansion in most of these types of derivations. So here, I've already written out the Taylor expansion for sine alpha. This requires a bit of derivatives and all that sort of fun stuff, but effectively we get something that looks like this for the expansion of sine alpha in terms of the alpha. We could go to third order, however, in this case I decided to go to fifth order, and obviously, as I wrote here, it's a better approximation, and we can still evaluate alpha analytically by going to fifth order. So, if we were to write, technically this should be approximately equal to this, as I'm taking only up to the fifth order term for the Taylor expansion of sine alpha. We then get this equation here, which then reduces, because we have a 1 over alpha here, to a polynomial of alpha to the fourth. All right, we can then rewrite our equation in order for us to produce a quadratic equation, which I then substitute in alpha squared for beta in order to explicitly make that look more like a quadratic equation, and reducing it slightly even more to make it even more apparent in that calculation. You'll find that I do a lot of substitution just to make things a little bit more compact and a little bit easier, hopefully a little bit easier to see the relationship to the standard quadratic formula that you would then apply to beta in order to solve for what beta is in terms of the quantity that we call B here, which relates the chord and the arc length. All right, so once we did that, we solve for beta, and then we get two values which correspond to the two roots of beta. All right, and if we use my particular spoon, I had a chord along the semi-major axis of 5.7 centimeters and an arc length of 6.2 along that same semi-major axis. So when you measure this, if you choose to use the semi-minor axis here, just make sure that you also measure the arc length along the semi-major axis when you do that. Here all I done was the semi-major. Sorry if I said the semi-major, this is semi-minor. The semi-major axis here should be the arc length as well as the chord. So just remember that when you're doing that measurement if you choose to do this particular method. All right, I get a B of 4 with this particular these particular values, and this gives me two roots that correspond to these two values here. Looking at those roots and evaluating them, if I look at the fact that beta is equal to alpha squared, that means alpha has, again, two roots, and we'll choose the positive one, since this one, we can't have, or we could have a negative angle, but in honesty, we'll just take the positive angle since they are both symmetric anyways. Evaluating these two quantities here, I then get these values here for alpha, and then solving for theta, which is just 2 times alpha, I get these two values here. So these are the two roots that you would get effectively. There should be 4 that the other two just have a minus sign, but we neglected those since we're just choosing the positive ones for all intents and purposes. We then choose 0.9 radians, since 8.8 radians is too large. It's much greater than, or I shouldn't say much greater, but it's larger than 2 pi radians, which is a full circle. You could certainly subtract off 2 pi and see what that does, but in this particular analysis, by using 0.9, I do get a radius of curvature of 6.9 centimeters, which was fairly close to the 7.1 centimeters. So, all right, that concludes the derivation and application of the finding for the radius of curvature of your spoon mirrors. And I hope you enjoyed it. And again, always stay safe and have a good day.